what this lecture is going to tell you is methodology for planning a refactoring process, the kinds of considerations that you ought to be thinking about before and during the refactoring process, how to develop a process and a schedule, and possibly tell you about the pitfalls and the workarounds that are there. In addition to that, I will give you examples from the code, from one code that I'm very familiar with, which has undergone a refactoring process, and also the lessons we learned in the process. What I am not attempting to do in this lecture is give you a step-by-step recipe of how to do a refactoring of your code. And the simplest reason for that is there is no general recipe that works for all codes. Every code has its own peculiarities and its own process, and every group has its own peculiarities and its own process. So everyone has to develop their own. And then also, unlike many of the talks earlier today that talked about tools that you can use, I am not going to talk about tools, and I'm not going to tell you the tools for refactoring for the simple reason that there aren't very many in existence. So you're pretty much on your own when you're trying to do this. So I've divided up my talk into sections: before starting, during refactoring, and then the example. So before starting, you should absolutely know why you are embarking on a process of refactoring. Do you really need refactoring? What is it going to buy you? Where do you want, and where do you envision your code ending up after the process of refactoring? Up ahead, before you even change the first line of code in your code, you should absolutely decide on the scope of refactoring. How deep are you going to touch your code? How many feature changes you're going to make, and know precisely where, the degree to which you want the change to happen. You should estimate the cost in terms of not just the time spent by various developers, but also if the code is also being used for production, there is going to be disruption in the process, and so you should take that cost also into account. So both the accounting for the development cost, the design cost, and the disruption cost, you should take those into account. And before you start on the process of refactoring, you should absolutely get a buy-in from the stakeholders, which is the code developers, the code users, whether internal or externals. They should all be on board with the process of refactoring. If not wholeheartedly, at least grudgingly, but they should be on board. It should not be going against people's desire, because then what happens is people don't like to change. And so, Barry?
Could you give a succinct definition of refactoring?
That is a hard one. Succinct. Refactoring is changing your code so this may not be a definition that everyone agrees with, but in my mind, refactoring is changing your code in a substantial way where some feature of it changes fundamentally, either the infrastructure or the capabilities change fundamentally. And the refactoring can be done for many, many reasons, and I will go into those reasons. But do you have a definition in mind, Barry?
I have heard people say that refactoring does not change the API of the code. Are you using that definition?
No, I'm not.
Okay, good.
I am not. It's all open. It's basically, for some reason, you are making a fundamental change to your code, and how deep you make that change is entirely up to you. So we may not want to call it refactoring if there is a formal definition, but this is fundamental code change. So, as I said, there can be many reasons for code refactoring, or code change, as you want to say. The biggest one that is going around these days is the change in computing platforms. This kind of major disruption happened once before when the computing paradigm changed from vector to RISC processors. And I will give you an example of the kind of code changes that needed to happen with fast Fourier transform, and exactly how the computations needed to change. But now, at that time, the memory model for accessing the memory was flat, versus when you went to the RISC processors, it became a hierarchical memory model. But now the change is much more pervasive. Now it is not just from one particular paradigm to another particular paradigm. Now it is from one paradigm to anything goes, because there is heterogeneity all over in the platforms. And not just that, the compute model itself is different, but also the memory models vary from one platform to another. Even if you have the same kind of CPUs, you can have a completely different memory organizations that you have to deal with in your code. Mind you, it's for most of these transitions, the driving factor is not that the code will not run. In all probability, you can make your code run. The driving reason here is that unless you take care of designing your code in such a way that it can do reasonably well on different platforms, you're just going to be running it very slowly, probably slower than you run your code now, and you will not make any substantive advancement. The other reasons for which you can have a code be refactored seriously or change fundamentally is, one is when the code changes from being a research code to a production code because the requirements from the code change. You may be, there is much less of a demand in terms of professional output from a code when it is a research prototype versus when it has gone into a production and is actually getting used to. When I say research prototype, I mean the code itself is the object of research, not that it is being used for doing some other research. When I say production, I mean that the code is actually being used to obtain research results in some domain science. And another reason why you might change the code fundamentally is you have a spaghetti code, you want to use it in a certain way, you want to expand the user base, so you want to impose some sort of an architecture and maintainability on top of your code. And the third reason another reason is you may want to, the model in which that code is getting used may change, in the sense that it may be a code that was getting used by a small group of internal users, and you want to release it to the world outside. So now the use model has changed, and therefore the code needs to meet certain minimum standards of professional requirements, and you might want to refactor the code. Another reason, one of the less, well, not so less anymore, is that supposing you find that you have a code which has certain kinds of functionalities that are being used to do research in one domain, and you identify that those same common functionalities are common for another domain, and you want to expand it to that domain, and then you want to make it possible for that kind of extension or expansion of capabilities to happen, so you might do refactoring. It can happen because of model refinement. You added more capabilities and you need to extend the functionality, or it can happen because of incorporation of new insights within the existing model. So before you start, as I mentioned, you need to know the scope of your refactoring. So you want to know where you want the end product to be, which means that you want to, if you're doing it for the purpose of improving the performance, you want to know when is enough. Because it's very easy to go down the rabbit hole of trying to squeeze the last little bit of performance out of it, which can be counterproductive in many cases. So you should know exactly where you want to reach. Again, for maintainability, you want to know the boundaries for how much structure you want to impose. Do you really want to rewrite the entire code? Often there are parts of the code where you can stop. For example, if you just have a formula that you've implemented in a small kernel, possibly you don't need to change that kernel. So you have to look for such opportunities where you can contain the amount of change that you want to make, because otherwise, again, it can go out of scope and become intractable. And when you are looking at reasons for extensibility, those are similar to maintainability. How much structure do you want to impose? How much structure you want to change, et cetera. You want to, when you're doing it for extensibility, of course, you want to give greater emphasis to interfaces and encapsulation, because the more you modularize and encapsulate, the easier it is to extend the capabilities to other parts of the code. Going back to the biggest reason for refactoring, and as I said, I would give you an example for what happened when change was made from vector to RISC computing. So the biggest reason these days people are looking to refactor their codes is change in platforms. So the transition that happened about 20 or so years ago, 20, maybe 30 years ago, was from vector to RISC machines. So vector processors, the ideal scenario was, and the way the vector processors operated was, they said we have this unit, which does this kind of processing, the following unit, which does this, the second kind of processing, a third kind of processing, and a fourth, and so on. And you just fed a long vector of numbers to each of those stages of processing, and it went from one stage to the next, to the next, to the next. And the longer your vector was with single stride, the better your performance overall was. So the incentive was to have as long a vector as possible. Now, vectors could be done either in the form of what is also called the SIMD code, which is single instruction multiple data, because that is in some sense a vector operation. But that is not the only way you can do vector operations. You can also do vector operations in a pipeline format, in the sense that you can feed data to a compute unit which will just do a single operation, and you keep sending one data after another, as long as the sequence of operation remains the same, and you're feeding long vectors of data into the machine. The way these vector machines access the memory was through memory banks, because what they wanted to do was they wanted to fetch in data from, they didn't want the bottleneck to happen in trying to reach from the single bank. So different data items came from different memory banks, but the access was completely flat, completely uniform. There was no cache, there was no hierarchy in the memory. From there, we went into RISC machines. Now, the RISC machines had memory hierarchy, and the biggest feature, so they had few instructions, but the biggest feature of the RISC machines was that the closer the memory is to the CPU, the faster it is and the smaller it is. Which means that instead of having a long vector for operation, your ideal working set was a small set that could fit ideally into the closest memory to the processor, which is the cache. And also, so you're not just looking for that spatial proximity, you're also looking for temporal locality, which means that once you fetch the data into the cache, you wanted to reuse it over and over again, and that is how you would get better performance out of the code. So what you wanted to do was you wanted to have as many operations as possible done into the data once it was fetched into the cache. And so the code, so if you look at the way the code had to change, it's simplest to explain it with an example of an FFT. An FFT is a collection of what are called the butterfly operations, one after the other. And the way these butterfly operations look like is here, as you can see, that first you do it with depending on how you've organized the code, this is one way. First you have interaction going on between the two consecutive data items, and then the next two consecutive data items, and so on. In the next butterfly, it becomes twice the stride. In the next stage, it becomes 4 times the stride, and so on, in terms of interaction among data. So when a vector machine operated, the ideal thing would be, and notice that the operation is you have x0 and x1, and they are combining through the use of an omega factor, and the outcome comes out on the other side. So in vector machines, what I wanted to do was you wanted to pre-calculate all of the omegas, and that continued in the RISC machines also, but you wanted to calculate all of the omega factors. And then you wanted to operate in one vector after another. So you fed the entire vector into the first stage. The outcome came, you fed it to the second stage after some permutation, you fed it to the third stage, and so on and so forth. You went through the permutation stages in between, but every stage was computed as a whole, and you send the data on to the next stage from the previous stage. In RISC calculation, that changes, because now what you want to do is you want to compute as many stages as possible on the data that you fetched in. So what's going to happen is you're going to block. So for example, if your cache is such that 4 data items can fit into it, you will do these 2 stages in the block. Then you will do, for the first 4, the top half of the butterflies. In the next step, you will do the bottom half of the butterflies, and then you will do a shuffle so that the butterflies are rearranged, and this shuffle example shows that, and then you will repeat this process. So now what you're doing is you're rearranging your data every time so that more than one stage is done once the data is brought into the cache, and that you are operating with a working set that is fitting into the cache. So this was a fundamental change. And as you can see, this was a change that had to be very deep into the code, because instead of writing vector operations, now you had to do the blocking. So loops needed rearranging, and extra nesting in the loops was needed. So this was the first example. Now, because of the heterogeneity, the changes are going to be where in some places, the CPU kind of operations are more, will get you better performance. In other places, vector operations will get you better performance. And you have to prepare codes in ways where both of these can coexist in the same code. And one of the talks tomorrow on design and process is going to elaborate much more upon how it is a possible way of architecting your code and arranging your data structures that will let you prepare for heterogeneous architectures. So that's not a part of this today. Today I illustrated this example just to show you the kind of deep-seated changes that you may need to know, that you may need to make into your code. Next, we move on to the planning and implementation. So when you're doing the planning and implementation, the thing that you have to do is be very careful in cost estimation, because it is usually the biggest pitfall. Typically, code projects overrun both the time and the cost that it takes. And it is notoriously hard to estimate the amount of time that it is going to do to work on a code that needs refactoring, especially if it is of anything other than a non-trivial size code. And there are many reasons for it. In a large code, there is usually not one single person who understands the entire code. And so they don't really understand the complexity that exists in different parts of the code. So they underestimate the overall code complexity. More than at the time of development, actually, verification and validation becomes even more critical when you're trying to do a code refactoring, because now you're not, you're coming with a history and you're making changes. And when you're trying to develop a code new, the process is different. But here, things can go wrong, not just in terms of individual units, but also in terms of how they're interoperating. And that can be very difficult to trace back unless you have developed a really strong testing regime. And that is the reason why this particular talk came after Alicia's testing talk, because you cannot do refactoring without having a very solid verification regime in place. So the factors that can help in this process of even cost estimation is knowing the scope, sticking to it. If for some reason in the middle of the refactoring phase you change the scope, it is absolutely necessary to go back and do the estimation process again, estimation of cost and time again. One has to plan for all stages with contingency factors built in, and make provision for developing tests and other form of verification, because that can be as much or more work than the code change itself. And the term, remember a term that Catherine introduced this morning, the term technical debt. If you do not, in the refactoring process, develop a good verification and testing regime, the technical debt that you incur is going to be really, really terrible. So this is something to keep in mind when you're doing the process development. The other thing that you have to keep in mind in cost estimation is that often when a code is getting refactored, it is also in production. So the production and the development branches, if you want to call it, of the codes need to coexist. And usually in scientific codes, in my experience, it is never the case that the production branch is not changing itself. So you have the code that you're refactoring where you're making deep changes, and then you have the working production code where you're making incremental changes all the time. And unless you have a good process in place, these two can diverge, and reconciling them can be a real nightmare. So this potential has to be recognized and planned for. There have to be policies for code modification in terms of if you want to, how far are you going to allow the divergence to happen, and how are you going to synchronize the branches that are diverging? How often, what cost are you willing to put up with in the process of keeping the two branches synchronized? And because you need to have the disruption in the production, and therefore some sacrifice from the side of science results coming out, that is why the buy-in is very important, because it is inevitable that there are going to be times when the code freezes are necessary in the production branch. So you have to account for those, and you have to have the buy-in from the stakeholders, otherwise managing the process becomes impossible. The other thing that you need to have, in addition to your cost estimation, scope estimation, is an on-ramp plan. An on-ramp plan is how are you going to change from one version of the code to the other version of the code. You can do on-ramp in two ways. You can do all at once, or you can do it incrementally, right? If you have a relatively small sections of the code that you need to refactor, it may be all right to do the all at once. Here, the small green blocks are representing the code sections that have been fundamentally refactored. And so if they happen to be sort of disconnected, sort of small, you can just do it all at once and merge them together, and that's not going to be really terrible. But if you need to do a complete code change in some way that touches bulk of the code, all at once is just not feasible. In fact, you should just be, you should just step back and just not do anything further with that code, because this is not going to work, not for any sizable code. So how should you do it? The ideal on-ramp plan is that you can do it in one of two ways. One of the ways is that you keep a close communication going between the production and the development branch, but you develop them, you do the development completely in isolation. And when you are reasonably confident with the developed code, you do a merge back slowly, step by step. So what happened was we had the finished code, and then we had the finished code here, and we took one piece of it at a time and merged it back into the original code. And that's how we got the code change done. So this was the on-ramp plan in one way. Another way possible to do the on-ramp plan is to build just the infrastructure out separately from the whole code, and then migrate capabilities. So I'm differentiating between infrastructure, and infrastructure is whatever manages your discretization, your I/O, your runtime environment, and so on, and the generic solvers such as maybe multigrid, maybe FFTs, as opposed to specific science solvers, such as in Alicia's examples, you saw hydrodynamics, burn, et cetera, et cetera. So those are what I term as capability, and the I/O, the discretizations, et cetera, I term as infrastructure. So the other way of on-ramping is to build your infrastructure separately. If you are refactoring the infrastructure of the code, then build that independently, and then bring over capabilities into the new infrastructure one at a time. So depending on what your end product is, whether you're changing infrastructure or not, you can go with the first model or the second model. But you absolutely have to do this incrementally. Otherwise, this is not going to work at all. So for whichever mode of operation you take in order to do the refactoring, verification is the critical component of refactoring, because the need for verification during a refactoring process is different from the need for verification on an ongoing maintenance mode, is different from the need for verification for a production ready stage, is different from the verification that is happening during the development phase of the code. So what you need to know in the verification process is map from here to there. What can happen is you have tests that work for your current way of code very well, which may not work for the way your code is going to look like. So now you have this challenge that even if you change the code and you run the same test here versus there, you still don't know how to verify that that produced the right answer. Or that the consistent answer, that is, the answer that is getting produced here is similar to the answer that is getting produced here. You have to, I mean, yes, manual inspection is always possible because ultimately it is the scientific judgment which declared that the answer produced by the first version of the code was right, and you can repeat that process for the second one also. But if you decide to do it manually, then it becomes a somewhat intractable process because then someone is going to have to manually inspect every one of these results generated and approve or disapprove them. What you want is you want some sort of an automation. And in order to do that automation, you may want to, for example, build a utility that can take the output produced by the by the original code and the output produced by the refactored code and give you an intimation whether they are roughly equivalent or not. So in order to do that, why this would be necessary is also another thing that Alicia pointed out in her talk, is that in scientific codes, we're dealing with floating point numbers, which means that you change the order of operations and your results will change. So you do not have bitwise reproducibility available to you. And so you have to devise tests which are aware of the error bounds, and you have to know your error bounds, and you have to work with tests that let you do that. So you have to check for coverage because now your entire code is going to change, and if you don't have any part of it covered, that you will never have any confidence. And so you need to check for the code, the source lines, as well as functionality coverage in the map from here to there. And you have to, wherever there are gaps, you have to make sure that you develop new tests to cover that gap. And you have to make sure that you have tests at different granularities, which means that you have to have a unit test, integration test, and integration tests also at different granularities. And you have system level tests as well. Then during the implementation phase, you absolutely want to have procedures and policies in place, because hopefully, if you've done your homework before the refactoring section of the work right, then you know where you want the code to go, and hopefully the developers who are going to do this know where they want the code to end up being. So, but for their job to be easy, it is necessary to manage the coexistence of production and development, have the policies for them, have the policies for managing branch divergence, look if there's any code that needs pruning, which means that if there is dead code that had been accreted, it's a good time to get rid of that when you're doing the code refactoring. You have to have a schedule of testing, and then you have to have a schedule of integration and release. And this doesn't just apply to open source codes. This applies even if your refactored code is going to be internally used. You still have to have a sort of release and integration in place, because you want to be able to signal to the users that this section of the code is now ready for them to use. So these are the general principles that you can apply for a refactoring process. And next I'll tell you a few things about experience from the Flash code. So Flash is a code that started its life as an astrophysics thermonuclear flashes simulation code. It was designed to simulate various kinds of thermonuclear runaways that happen, which is novae, supernovae, et cetera, So it needed to have certain of the physics capabilities, such as compressible shock hydrodynamics, such as nuclear burning, and specialized equations of state, et cetera, that it needed to be able to combine in many different ways to use the same code base to generate different applications, right? So it was built from the ground up with certain amount of configurability in its place. But the version 1 was a smash of 3 completely independent codes that came from 3 completely different groups with different coding practices and different coding standards. So there was, and so there was what I call the good, the bad, and the ugly in version 1 of the code. The good was that there was configurability because they wanted to use the same code for doing many different applications. So there were alternative implementations, and some sort of a plug-and-play capability was there right from the beginning. The code was written in Fortran 77, but the early developers of Flash wanted to have some sort of an object-oriented model of development. So what they did was they used inheriting Unix. So they turned the Unix directory structure into the inheritance mechanism. And we don't need to go into the details of that. You can read the Flash architecture paper if you want to know more about it. It's just enough to know that that's how inheritance and object-oriented code was implemented. The bad was that it was Fortran 77 style of programming, which means that there were common blocks all over the place. You didn't know where the data originated. You didn't know what its scope was. You didn't know who should be modifying the data and who shouldn't be modifying the data. And you didn't know. Fortran 77, if you've ever looked at the code, you know that the variable names are never intuitive. The variable names are A, IJ, IK, IX, IMAP, et cetera, as small as they possibly can be, as cryptic as they possibly can be. So you really didn't know the source variables. You didn't know what they were doing. And the ugly was, and this is a problem that happens in almost all scientific endeavors, is that there are conflicting desires. There are scientists who wanted to have a code that they could use for production right away, because otherwise their results were waiting. And there were people who, and this is the time when software engineering was not even considered something of any importance in the computational science community. And even the frameworks were funded research, which means that no knowledge existed about what you could do with modularity, et cetera. And so there was this camp which wanted to do it right, build it modularly, build it with some sort of a structure. But there was no literature, there was no proven record of that kind of an effort succeeding. So for a while, both camps went on in parallel. But then, of course, there weren't enough resources. So the camp one won out, which is the scientists wanted the code. So it started off that way. So capabilities kept on getting added while F77 remained. So remember the reasons for doing major refactoring. So what happened was that limitations to extensibility were becoming obvious in Flash version 1, so it was decided to refactor the code and turn it into Flash version 2. Notice that, mind that the scientists were still in control. So they wanted to be able to use the code at all times. And the scope that in Flash 2 people decided to have was they were going to inventory the data, and they were going to turn it into a centralized database so that they'd know exactly where the data came from. But the constraints imposed on the developers were that both the codes needed to be in sync at all times, which means that anything that was added to Flash 1 had to be replicated in Flash 2. Because there was no restriction on what could be added into Flash 1. There was no code freezes. Flash 1 was going as though it owned the universe, that it didn't have to deal with Flash 2 at all. So centralized database was built. The objectives were partially met in the sense that data did get inventoried, but modularization did not happen, encapsulation did not happen, and extensibility did not happen. In fact, what was even worse was, because of the centralized database, if anything, the origin and the scoping of data was even more obfuscated than it was in the original version of the code, because now everything just resided in one place, and you had no idea who could be modifying. Everyone had equal access to every bit of data in the code. Anyone could fetch it, anyone could modify it and put it back in. And the structure got so confusing that the on-ramp time for new developers was impossible. It took 6 months before you had the confidence to make a check-in to the code, because you didn't know where, you're working in a mesh unit, and all of your functions are in the mesh unit, but all of the data that belongs to the mesh is sitting under a completely different part of the source tree under a database. So it was absolutely confusing. So we did the second major refactoring, and this is when the lessons learned from the refactoring from 1 to 2 were applied. So the first thing in version 3 that was done was applied encapsulation. Devise a unit architecture, divide up who owned what data and what access it wanted to give to the other units. The APIs were defined, the data scoping was defined, a unit was defined, and so on. So the naming, another important thing that happened was that naming conventions were defined where the names were such that the source of the data was part of its variable name. So if it was a data that was dealing with grid, the unit was grid, so it would be grid underscore whatever its functionality was going to be. So irrespective of where you saw that data, you knew where it came from. The unit architecture, as I said, was formalized. The data ownership and scope was resolved. So there was unit scope data, there was subunit scope data, and that data just belonged to that particular unit. It wasn't globally available to all of the other units as well. Lateral dependencies were resolved and encapsulation was done, and sometimes they were very, very non-trivial because, for example, between grid and I/O, you want a complete access to the data for performance purposes, and therefore there are these lateral interactions that you have to allow for, and you still want an encapsulation of some sort. And those were different challenges. Again, you can read the papers related to flash architecture to read this in more detail. That's out of the scope for this one. But this is the time when we also built the subunits and a built-in unit test framework. And unit tests in Flash parlance are different from the unit tests as they're understood in the general software. In Flash, a unit test is if you can test a particular functionality against an analytical or a semi-analytical solution, or a solution generated by using some other mechanism, instead of comparing the results against previously approved results. So that's which a unit test in Flash in that sense is a limited capability test, which is a self-contained test. It does not depend on producing results and comparing results against previously approved answers. And then so Flash 3 turned out to be a very successful transition. Even there, we knew the scope in the sense that none of the kernels were getting changed. So the computational kernels were not changed. It is only the architecture and the infrastructural aspects of the code that changed. But that was successful enough that this change was completed in 2006. And up until now, when the heterogeneity of the computing platforms has made it impossible for this code to persist in being a performant code on high-performance computing, it has just grown, and only the capabilities have needed to be added. No substantial changes have been done to the infrastructure or the architecture of the code. And from astrophysics, now it is serving 6 other communities. They include cosmology, computational fluid mechanics, fluid structure interactions, high energy density physics, laser experiments, laser plasma, biomechanical systems, and solar physics. And these are the ones we are aware of. There may be others who are using it in different, and I'm sorry, industrial combustion, that's another one. So in the version transitions, what happened, what were the lessons learned? In version transition from 1 to 2, objectives were partially met because the bias was to keep the scientists in control. And the reasons for only partial success were there because the process wasn't agreed upon up front, because there was too much synchronization between branches. Deep changes that needed to happen could not be done. As I said, hugely increased developer effort and high barrier to entry. Not enough buy-in from the users was another very big reason why that only met its goals partially, in the sense that people still kept using Flash version 1.6 for production 2 years after Flash 2 was ready. This was one of the lessons we really took to heart. So when the transition happened from version 2 to 3, the framework was built in isolation from the production code. The ramp-on was planned. So we had a complete methodology planned out for how the transition was going to happen. That infrastructure, so we had this ability, Flash is an AMR code, but an easier version of dealing with the discretization is to use the uniform grid. So we built the uniform grid, built in the test suite, started testing it on a regular basis, used the physics capabilities, used the unit test to test for physics capabilities separately, and then brought in AMR. The solvers that were not getting changed very often were the ones that were brought over first. Then the next round was that instead of trying to, one migrated all of the solvers that were needed for an application to start being able to be able to run in production mode, because code starts to get stress tested in production mode much more than in any other way. So that's how we made the transition. And in the end is when we moved the units that were under active research, that were undergoing a major amount of change. But by that time, within the center, the version 3 had become the production code of choice. In fact, Flash's research had switched to version 3, I think at least 6 months before it was released to public. Public still had version 2 until then. So the takeaway from this talk, and this you could think of as a recipe for refactoring if you want to at a very high level, is to have a good outcome from refactoring, you should know why, you should know how much, you should know the cost, you should plan your process, the policies, the on-ramp, everything, have very strong verification and testing regime, and get buy-in from stakeholders. Without this, your refactor is not going to be successful. Questions?
When doing the refactoring part, so for the testing, so this means you're going to refactor the test too as part of refactoring the code, right?
If that's what is necessary, yes.
If you do a major API change, then some tests actually will retire with this API change because this test won't work anymore.
This is true.
Okay. So how much does that add to the cost in general?
Depends upon, like I said, it all depends upon the scope of your transition, right? Because if your API is only changing at the level of, like, it can happen that your API changes, but the output that you're generating in terms of your state is still the same, right? And if that remains the same, then all you need is a utility that understands the error bar, and your test will still be valid. Whereas if you're changing the algorithm in terms of your API, then you may need manual intervention. So like I said, there is no set rule. You just have to understand what your requirements are and build your tests accordingly.
Do you think that favors like building kind of more integration tests than like very small unit tests? So basically when the refactor takes on like lower level of the hierarchy, you don't have to rewrite a lot of tests because like the APIs that say it's on top don't choose as much as the APIs as like more in depth.
Like I said, I will not go so far as to say one is better than the other. It is entirely going to depend upon the depth to which you're changing things. So it may be that all of if your changes are, for example, in Flash, when we did versions 2 to 3, all we really needed to do was to change the reader for the output. But the values generated in the state were identical, and therefore we could use those. But we had to change the unit tests completely for the infrastructure, because the previous infrastructure and the new infrastructure had nothing in common. So they had to be completely different. Whereas now, if we want to make the change to Flash, where now the change we are looking at is leaving the infrastructure and the backbone as it is, but change the kernels because they need to be solver independent, they need to be platform independent. So now it's our output, the state output, that is going to look different. So the unit tests will still be valid for the infrastructure, but our state output tests need to be different, and they need to rework their error bounds in order to match the results.